Hypothalamus artificial intelligence. Digital transformation powered by real-time autonomous and intelligent algorithms. High-power, autonomous optimization software for electric sector enterprises. Is an optimization decision support system oriented to agents acting in electricity systems, electricity wholesale markets, and smart grids. High-power, autonomous optimization software for electric sector enterprises. Is an optimization decision support system oriented to agents acting in electricity systems, electricity wholesale markets, and smart grids. High-power integrated the following models. High-E electricity supply chain optimization supports decisions in the electricity supply chain, in terms of sectoral planning and business generation. High smart grids optimization supports the decisions of the various agents involved in the smart grids business. High natural gas supply chain optimization supports the decisions of the actors involved natural gas supply chain at the level of sectoral planning and business generation natural gas. According to the structure of modern electricity markets, the support of the business decision-making power generation should be seen from several points of view. Central agents, formed by the regulator, supervisor, planner, and system operator. Generators, agents that operate power plants. Distributors, utilities enterprises. Traders, smart grids operators, and industrial companies. High L and high SGO cover all levels of the electricity systems. Electricity system and wholesale market optimization models. Hydro system physical modeling. High water corresponds to a general model that includes all kinds of hydraulic components, reservoirs, hydroelectric power plants, rivers, overflow channels, connection points and pumping stations, demands, like irrigation, aqueducts, environmental, industrial. Components can be freely linked to form any topology, like pumping storage systems. Hydroelectric power plants are modeled independently of reservoirs, so plant-reservoir connectivity must be established. The regulation capacity of the reservoir is simulated in detail, so such a simulation consistently represents the dispatch of the power plants, considering their ability to regulate the multi-annual, annual, hourly water resource. Electric system physical modeling. Electrical connectivity is carried out through a network of circuits and bars that integrates different types of installations, power plants, like hydroelectric, thermoelectric, coal, wind, solar, biomass, places of demand, like industrial, cities, regional interconnections and energy storages. High power includes the simulation and several types of renewable energy sources and energy storages. For each type of electrical asset, high power includes the exact equations for simulation. Natural gas system physical modeling. High gas describes the process of supply and demand of natural gas. From this point of view, its integration with the electricity system determines the economic equilibrium electricity-gas markets. The entities of the natural gas system are: node, connect the gas system installations; production fields; consumption zones, discriminated by sector, example, refineries, heavy industries, residential, vehicular, and commercial thermoelectric power plants; transport systems, pipelines, and multimodal transport systems using vehicles, pumping stations, compress the gas to transport it, and ports, receive and ship liquefied natural gas, LNG, and have gas storage capacity. Connectivity between the electricity and gas sectors occurs through the demand for natural gas for use in thermal plants, and the substitution of the demand that can occur between gas and electricity. Electricity system and wholesale market mathematical models. Make up a flexible decision support system that provides different types of services in an integral way. They can be classified into integrated dispatch of generation plants, optimization of generating agents, and predictive analytics of stochastic processes. Traditionally, the optimization models in the electricity sector consider individual modeling with exogenous coordination between models, based on multi-stage stochastic programming, and using large-scale optimization methodologies. The differences with the state-of-the-art modeling, provided by high power are integrated holistic modeling, scientific risk modeling, multidimensional uncertainty, parallel optimization, and autonomous real-time distributed optimization. Three types of connectivity of the generation system and the transmission power grid are considered: ideal single node, ideal dispatch ignoring the transmission system; Electric transmission network connectivity based on the detailed connectivity of the electricity transmission system using bars and circuits. Operative areas connectivity, when the user does not have, or does not want to use, the detailed configuration of the electricity transmission grid. It is possible use the connectivity based on operational area //app. Blaster online. com/speech low/ changelogs including limits on the transfers between areas. Interconnection electricity, gas integrates electricity network with natural gas network. Interconnection of electricity and water can be fully detailed, including travel times between nodes and transport restrictions in water resource conduction channels. The central model of high power is the standard representation of the electricity and gas supply chains. These equations give rise to variations of the model according to the techno-economic concepts that support a specific modeling. There are at least 4 types of economic models to represent the electricity and gas market. Economic perfect dispatch, EED. Economic regulated dispatch, ERD. Nash-Carnot equilibrium dispatch, NCD, and unit commitment, UC. The EED is the core model of high power, as its equations/constraints are used in multiple specific models that the agent requires to address decision support needs. EED and the UC models optimize the dispatch of generation infrastructure, minimizing the cost of operating the electricity system, which simulates a perfect electricity market. The differences between these two models are the detail of modeling. EDD is oriented to planning and UC to real dispatch. Economic regulated dispatch, delivery of plants that minimizes the cost of operation of the interconnected system and includes representatives aspects of the regulatory of the electricity market being simulated. It does not correspond to a model of economic equilibrium, however, it is an easy and fast way to represent regulatory considerations based on optimization models. Nash-Carnot equilibrium, dispatch of plants oriented to the simulation of competitive electricity markets with agents that can influence with their decisions on transactions occurring in the market. It can be used to, among others, project the dispatch of a competitive market and study the exercise of dominant market power of agents. 4 models are considered fundamental to support the strategic, tactical and operational decisions of an agent that operates generation plants. The diagram presents the design of an integrated set of mathematical models to support the decision-making of a generator agent. Electricity dispatch and financial analysis. Integration dispatch models with assets liabilities management, ALM, financial models including risk management, to perform analysis of the financial impact of decisions. The main applications are the valuation of income and expenses of investment projects, energy installations, and valuation of energy companies, and integrated optimization of investments by global energy companies, taking as a reference the regulatory laws of the different regions or countries. The financial modeling results individualize the operating income and expenses, and can include all types of legal accounts. Electricity supply chain design and risk management, associated with strategic planning decisions related to resilient design of supply chain, in relation to capacity of reservoir, transfers, power plants and other assets of an electrical system. It may include risk management and financial planning. Energy trading and risk management. Optimal decisions related to trade energy and coverage of financial risks based on standardized or no bilateral contracts. It corresponds to a set of mathematical models aimed at supporting the decisions of the different agents involved in energy trading in long-term market, spot market, and secondary markets. The result of a risk analysis is the definition of Pareto curves of risk versus expected revenue, based on which the decision maker must define the risk position he wishes to assume, varying between risk-prone and risk-averse. Maintenance optimization is oriented policy making preventive maintenance of multiple central generation plants and others electrical assets. It can be applied to all assets in a regional or national grid. High power man can be implemented following the principles of PHM, prognostics health management, for industrial asset maintenance, integrating specific models of predictive analytics for asset components and prescriptive analytics to optimize the integrated operation of the asset network. High power has been used by ISO, in Peru, and Market Supervisor, in Colombia, for planning and decision-making purposes. High power includes some predictive analytics models. Spot price modeling. The prediction of spot prices of the energy market is fundamental for the decisions made by an agent that participates in that market, whether buyer or seller, generator, trader, or distributor of energy. This is because the decision maker requires that the model's results that produce spot prices be used in other mathematical prescriptive models. The mathematical models to be used depend on the planning period, short, medium or long term, and the type of market considering the dispatch of the plants, by mathematical model, or by market agents offers in a free market. In free markets the situation is complex since the law of price formation cannot always be explained based on mathematical rules, explicit, clear and universal, that may integrate a mathematical model. Synthetic generation renewable energy sources. For the generation of synthetic scenarios of climate variables, there are two requirements: short-term, hours, days, and medium/long-term, weeks, months. Specific short-term models must be built for each renewable source. For the medium and long-term, there are three alternatives to generate synthetic scenarios. Synthetic statistical model for the generation of climatic variables, firing Metallis type. Generate synthetic series of climatic variables based on the mixture of historical series. Generate synthetic series based on the historical series having the ENSO series, El Niño Southern Oscillation, as an instrumental variable. Projected short-term hydrological contributions using variations and enhancements of Kalman filter. Smart grids optimization models. In a regulated environment, generation, transmission, and distribution are operated by a vertically integrated enterprise, usually a state-owned, which has a monopoly on the supply of electricity. Conversely, in a deregulated environment, different parts of the electricity grid are owned and operated by different actors, and electricity markets provide a platform that fosters competition among participants. As each smart grid is, it requires a specific decision support system that allows the operator to interact with the entire electrical system. HiSGO provides all the analytical elements necessary to configure the specific DSS that each case requires. Forecast renewable energy sources. They correspond to predictive analytics models focused on the prediction in the specific sites where are located the generation plants. Forecast of demand energy. Demand projections per years, months, weeks, days, hours. HiSGO is integrated by the following optimization models. Economic dispatch of the smart grid, optimization of the management of electrical energy in small cities, factories, universities, shopping centers, office buildings, urbanizations. Smart grid unit commitment, optimization of the dispatch of the electrical load in real time, or in the short term. Smart grid configuration, optimizing the network topology. It considers voltage control, configuration of feeders, location or activation or reallocation of electrical assets, like transformers, capacitors, and phase balancing. Smart grid design, optimization of the design or redesign of smart grids with modern power technologies. ETRM, electricity trading and risk management, decisions to buy and or sell electricity, in a long, medium and short-term market, one day in advance or the day of dispatch. Industrial energy efficiency. The technical economic viability of energy storage coupled with the proliferation of energy technologies based on renewable energy sources has changed the landscape of the industrial sector, since it is now possible, and increasingly efficient, to generate renewable energy and store it for use in due time. In practice, all industrial companies can be agents that interact in the electricity market, acting as co-generators and carry out commercial activities and transactions. This, together with the industrial Internet of Things, increases the pathways to achieve industrial energy efficiency. Industrial energy efficiency results of the integration of production processes, transformation of matter, with industrial energy services, energy transformation, aimed at the simultaneous optimization of both industrial production and energy conversion that is related to polluting emissions of gases and liquids, associated with increasingly demanding environmental control laws. The high-power and HiSGO models can be integrated with complex industrial process models, in which it is necessary to redesign the power supply system according to the new power technologies. This type of model includes the simulation of polluting processes, for example, combustion in furnaces, to determine the optimal mixture of fuels in accordance with environmental regulations. High power and HiSGO integrate the models and information systems around a common data model. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.